Today we are going to talk about stability of a feedback circuit. From previous episodes, we saw return ratios many times. We knew the return ratio represents the nature of a feedback circuit because when calculating return ratio, we set the input as 0. Similarly, the stability of a circuit can be also checked by the return ratio and has nothing to do with the input. Let's review the transfer function of a feedback circuit. It's A infinite R over 1 plus R, followed by D over 1 plus R. The intuitive way to check the stability is to see if there are zeros of 1 plus R on the right-hand plane or on the imaginary axis of the complex plane. To check the location of zeros, we can solve the equation 1 plus R equals 0 to see if there is any poles on the right-hand plane or on the imaginary axis. Or we can use argument principle. Argument principle basically said you can make a closed contour C in a complex variable S plane and start pouring the complex numbers on C clockwise into the 1 plus R function of S, which creates a mapping trajectory on the W plane. By counting how many times the trajectory encircles the orange of the W plane, we can speculate how many zeros and the poles of 1 plus R are inside the contour C. If there are Z0 and P poles, the trajectory will encircle the orange Z minus P times. For instance, when 1 plus R has 3 zeros and 2 poles inside C, from the argument principle, we can expect the trajectory will encircle the orange 3 minus 2, namely once, in W plane. How would the argument principle help us to check the stability? Since we can decide the path of contour C, why don't we make it from minus infinite to the plus infinite on the imaginary axis, and then encircle the whole right-hand plane with infinite radius and then finish the closed contour C? The interesting thing happens when you substitute an complex value S infinite far away into 1 plus R. It usually converges to a finite value or 0, which means the trajectory in W plane only moves from substitute S from minus infinite to plus infinite on the j omega axis, which means we can check orange encirclement number by drawing the plot of 1 plus return ratio R as a function of j omega, where R as a function of j omega is exactly the frequency response. The times that 1 plus R function of j omega encircle 0 is equivalent to the time R function of j omega encircle minus 1. Notice that we assume there is no poles of return ratio R in the right-hand plane or on the imaginary axis. 1 plus R won't have right-hand plane poles and P equals to 0. This means the encirclement number N equals to Z. That is, if R function of j omega encircle minus 1 once, there is 1 0 of 1 plus R on the right-hand plane, which makes the function unstable. This is why when we check stability, we will use phase margin as an important parameter.